Hey everyone, and welcome to The Explainer. Today, we're looking at a truly critical shift in sustainable construction materials. We're going to explore how a fast-growing tree is literally being engineered from the ground up to support the buildings of tomorrow. It's a real game changer, and it is completely transforming the timber industry.
So, right off the bat, we have to ask a massive, high-stakes question. How do we build sustainably when our natural forests are rapidly disappearing? The construction industry is booming globally, and builders are absolutely desperate for materials that don't compromise on strength. But here's the catch. The natural, old-growth timber we've traditionally relied on to build our homes and cities, it's running out. We're facing this severe macro problem where demand is just skyrocketing, but our natural forests simply cannot keep up without facing total devastation.
Okay, let's dive right into this. Here's our agenda for today. First, the global timber crisis. Then, enter the Acacia hybrid. After that, we'll cover what LVL actually is, followed by the resin recipe test, the strength and swelling results, and finally, building a sustainable future.
All right, Section 1. The global timber crisis, depleting natural resources.
There's an incredibly urgent need for alternatives in the wood-based industry right now, especially in places like Malaysia, where natural forests have been heavily depleted over the years. But this scarcity isn't a dead end. Not at all. It's actually a powerful catalyst. It's pushing the entire construction industry toward highly innovative engineered wood products. Basically, we needed something that grows fast, in dedicated plantations, so we can finally leave our remaining natural forests alone.
Moving on to Section 2. Enter the Acacia hybrid, the fast-growing hero.
Let me introduce you to the Acacia hybrid. It's a cross between Acacia mangium and Acacia auriculaformis, and honestly, it's an often overlooked powerhouse. I mean, look at these stats. It boasts a remarkably rapid growth rate and adjusts perfectly to tropical climates. But more importantly for construction, it has this moderate density combined with highly favorable bending strength. Plus, its anatomy is just perfect for being sliced into really thin veneers. Ultimately, it provides a highly reliable, renewable raw material for builders.
Which brings us to Section 3. What is LVL? The transformation. So this is where we take that raw plantation timber and essentially give it structural superpowers. The secret is Laminated Veneer Lumber, or LVL. You can kind of think of this process like stacking the layers of a cake. You take those thin sheets of Acacia hybrid wood we just talked about, coat them in adhesive, and then stack them up so that the wood grain in every single layer is running in the exact same parallel direction. And this parallel gluing process, it is brilliant engineering. By doing this, it takes the natural inconsistencies completely out of the wood. What you get is a product that is actually stronger, vastly more predictable, and way more dimensionally stable than traditional solid wood. It literally takes a fast-growing plantation tree and turns it into a highly durable beam capable of handling heavy, load-bearing structures in modern buildings.
Okay, Section 4. The resin recipe test. Fine-tuning the engine. Now that we have our engineered Acacia LVL, we need to fine-tune its performance. And that performance relies heavily on the exact recipe of the glue holding the whole shebang together. Now, what's really interesting about this is a groundbreaking 2026 thesis by Mohammed Sharul Nizam bin Majid at University Technology Mara. This study dives deep into optimizing urea formaldehyde, or UF resin, to figure out exactly how much adhesive makes this wood as strong as possible. To find the answer, the researcher took a highly precise scientific journey. Step 1, they prepped high-quality, defect-free Acacia hybrid veneers. Step 2, they applied the UF resin. Step 3, they bonded it all together using a massive hot pressing machine to cure the glue. And finally, Step 4, they subjected those newly minted panels to a really rigorous series of mechanical and physical tests.
The core of this study was essentially the ultimate face-off between two different resin spread levels, 100 grams per square centimeter versus 200 grams per square centimeter. The goal here was finding the perfect balance. We absolutely need enough resin to create incredible structural strength, right? But if we use too much, those glue lines become thick and brittle, the performance actually drops, and the manufacturing costs completely skyrocket.
Let's look at Section 5. Strength and swelling results, the data breakdown.
And this brilliantly illustrates the results. The statistical analysis from the study revealed very clear mathematical splits in the data. For some structural properties, changing the amount of glue made a massive, highly significant difference. But for others, it didn't matter at all. So let's cut through the noise and break down exactly what changed.
The amount of UF resin significantly changed three key things. First up, the modulus of elasticity, which is basically a fancy term for the wood's bending stiffness. Second, the modulus of rupture, which measures its maximum bending strength before it snaps. And third, thickness swelling, which is exactly what it sounds like, how much the wood expands when exposed to moisture. The spread level of the glue had a major, undeniable impact on all three of these structural traits. But conversely, the data showed something pretty surprising. Doubling the amount of glue had basically zero significant impact on compression strength, meaning the wood's ability to resist being crushed flat, and it also didn't change its overall water absorption.
So the absolutely crucial point here is understanding why those specific traits didn't change. Well, the physical logic is actually quite simple. A wood's compression strength relies way more on the natural, built-in density of the acacia wood itself rather than the layers of glue sandwiched between it. And as for water absorption, well, cured urea formaldehyde resin isn't completely waterproof to begin with, so slathering twice as much of it on the wood doesn't magically stop water from naturally penetrating the wood's cellular structure.
Finally, Section 6, Building a Sustainable Future, the Big Picture. So how does all this micro-level, glue-spreading science actually connect to everyday architecture and construction? Perfectly, as it turns out. By figuring out the optimal amount of resin, the industry can manufacture Acacia LVL that is highly cost-effective and structurally reliable. We can confidently use this fast-growing wood to build safer, stronger structures, which directly and drastically reduces our dependency on imported species and literally saves our old-growth forests. Which leaves us with this final, lingering thought. We've just seen how a tree that grows incredibly fast can be meticulously engineered into a building material that actually rivals solid old-growth timber. If a fast-growing hybrid can be engineered to sustainably build our future cities, what other incredible, sustainable secrets is nature hiding right in plain sight? Just something to think about. Thanks so much for joining this explainer. We'll see you next time.